Hello everyone, I hope you are well. This video will cover section 16.1 to 16.3. Much of this you've already covered. The Arrhenius definition of an acid and base simply deals with what it produces when it's mixed with water. An Arrhenius acid produces hydronium ions in water, and Arrhenius bases produce hydroxide ions in water. Lewis acids and bases are electron pair acceptors and electron pair donors. The main definition that we're going to be working with are the Bronsted-Lowry acids and bases, proton donors and proton acceptors. This is the theory we'll be focused on. We should be familiar with the hydronium ion, H3O+, and that is formed when an acid donates an H+ to a water molecule. Again, all of these reactions are occurring in water. When you see H+, or if I mention H+, we're really talking about hydronium. So H+ equals hydronium for all intents and purposes at this point. As far as conjugate acid-base pairs, we've covered this already. You have to be able to identify your acid and base first. So, for example, your Bronsted-Lowry base, water in this case, gains a proton. Every base has its conjugate acid, and every acid has its conjugate base. Do you notice how HCl has lost a proton? The acid has lost a proton, and on the other side of the equation, we can identify its conjugate base, the chloride ion. Let's look at exercise 1. On the following reaction, identify the acid on the left and its base on the right. Similarly, identify the base on the left and the conjugate acid on the right. So first, let's identify the acids and bases. HBr, what happened to it? It has lost a proton, donated a proton. It is the acid. And if we look at NH3, NH3 has gained a proton or accepted, making it the base. To identify the conjugates, let's go back to HBr. HBr has donated a proton, so every acid has its conjugate base. And for NH3, every base has its conjugate acid. For number 2, it asks, what is the conjugate base of H2S? Well, let's assume that H2S is the acid, and if a conjugate base and acid only differ by an H+, then the conjugate base would be HS-. See how I took away an H+? If we're asked number 3 for the conjugate acid of NO3-, then we are looking simply for its conjugate acid, HNO3. Notice how I've added an H+. Amphoteric substances are anything that can accept or donate protons. That's really the extent of what I want you to know right now. But water is amphoteric and it can accept and donate. Any anions that have a hydrogen, meaning it has a negative charge and a hydrogen, is amphoteric. NO3- cannot because there's no hydrogen to donate, and H3O+ cannot accept another proton. The relative strength of acids and bases. All right, so we're going to work with this chart here for a bit. The key concept is the stronger the acid, the weaker its conjugate base. Stronger the acid, the weaker its conjugate base. Look at the top here. We have our strong acid, say strong acid at the top, and its conjugate base on the other side is weak. Now we have very weak acids down at the bottom. That means their conjugate bases are very strong. So strong acids, you should know, are substances that dissociate completely into ions in water. They transfer all of their protons. We have 100% ionization. Weak acids, on the other hand, do not dissociate completely in water. They exist primarily in the unionized molecular form, but we have a double arrow, which means that an equilibrium exists. Both the forward and reverse reactions are occurring. This is incomplete ionization. Strong bases, like sodium hydroxide, dissociate completely, 100% ionization, and weak bases do not ionize completely. That's again why we use the double arrow. They only partially ionize. So let's look at some of the skills we're going to need to use when comparing relative acid and base strength. Number one, let's use relative acid-base strength to determine the position of the equilibrium. And the second skill is going to be to use the equilibrium constant to identify relative acid-base strength. The key concept here is the equilibrium favors the formation of the weaker acid and base. So we'll come back to this, but this is our main concept to solve this first problem. Let's look at the example. It says, using the table, determine if the equilibrium favors the reactants or the products from the reaction below. To solve this, we're first going to identify the acids and bases. So look at H3PO4. It has lost a proton. That makes it the acid. F-, it has gained a proton. Makes it the base. Every acid has its conjugate base, and every base has its conjugate acid. Step one, we identify the acids and bases on both sides. Step two, let's focus our attention on the acids only. Now that we know what our acids are, we're going to look at the chart on the right, find them. H3PO4, and we have HF. We see that H3PO4 is the stronger of the two acids. HF is lower on the chart, so it's weaker. All we care about is identifying the stronger or weaker acid, because fortunately, the weak ones are always on the same side. So now that I know what the strong and weak acids are and my strong and weak bases, I can use the concept above to determine what side the equilibrium favors. The equilibrium favors the formation of the weaker acid and the weaker base. So the weak ones are on the right side, or the product side. The equilibrium favors the products. Let's look at exercise 2. Same concept. We're going to use the table to the right to do the same type of analysis. First, identify the acids and bases. So look at HSO4. HSO4 loses a proton. That means it's the acid. See, it has lost a proton. Carbonate has gained a proton. That's the base. Every acid has its conjugate base, and every base has its conjugate acid on the other side. Just like last example, we're going to focus on the acids only. Let's find them on the chart. HSO4-, look only at the acid column. Ignore this conjugate base business for this analysis. Now let's find HCO3- right there. Clearly HSO4 is stronger. HCO3- is weaker. We know the weak ones are on the same side. So, weak ones ones are on the same side, strong ones are on the same side. And the concept to know is that the equilibrium favors the formation of the weaker acid and base, so the weak ones are on the product side. The equilibrium favors the products. So we've just seen two examples of our first skill, using relative acid and base strength to assess the position of the equilibrium. Before we get to skill number 2, we need to get a little bit of information about the equilibrium constant K. I would typically teach a little bit of chapter 15, so I'm just going to talk about it here. It's pretty simple. Equilibrium means a reaction in which both the forward and reverse reactions are occurring. Let's look at our simple reaction. Equilibrium simply means that the rate of the forward reaction equals the rate of the reverse reaction, not that the concentrations are equal. We can set up something called an equilibrium constant expression, which I'll explain why this matters, but K, EQ, is your equilibrium constant, or just K. So let's take a look. It's the concentration of the products over concentration of the reactants. B is your products, A are the reactants. Oh goodness, that's wrong. Typo. There we go. Sorry about that, guys. Products over reactants. Okay, so what does this tell us? The magnitude of K tells us what side the equilibrium will favor. So when K is greater than 1, if the value of K is greater than 1, that means that your numerator must be larger than the denominator. The numerator, your products, B. So that means there's more products. The denominator, or your reactants, A, that means there must be less. So when K is greater than 1, the products are favored. When K is less than 1, the reactants are favored, because your reactants, to get a value of K less than 1, your denominator must be larger than the numerator. So with that information, we can go ahead and try to solve the next type of problem. It says, identify the stronger and weaker acid and base on both sides of the equilibrium. Well, our clue here to tell us what side the equilibrium favors is looking at the K value. Because K is greater than 1, that means the products are favored. And if the products are favored, you can now determine where the weak and strong acids and bases are. Remember, the equilibrium favors the formation of the weaker acid and base. So the products are favored. That means that your weak stuff, the weak acid and base, are on the product side, and the strong acid and base on the reactant side. So now let's identify the acids and bases. HX has lost a proton, that's your acid, its conjugate base, and Y minus is the base because it has gained a proton, and we know on the other side HY is its conjugate acid. So now we know what the weak acid and base are. HY is your weak acid, X minus is your weak conjugate base. All right, exercise 3 is the same exact scenario, except K is less than 1, so we know the reactants are favored. And that means that the weak ones are on that side. Remember, the equilibrium favors the formation of the weaker acid or base. And the product side is the strong side. The K value told us that. And the concept before was that equilibrium favors the formation of the weaker acid or base. So my reactants are weak. Let's identify the acid and base on both sides. HX is your acid. Do you see how it has lost a proton, making X minus its conjugate base? And Y minus has gained a proton, making it the base. And we know then that HY is its conjugate acid. The question says, which of the following species is the strongest base? Well, the strong side is your product side. That's what our K value told us. And I know that X minus is the base on that side. So I've just identified the strongest base. The last problem here, dealing with this concept, just deals with a little bit of terminology that you may not be familiar with that I would like to explain. It says the reaction represented below is observed to proceed spontaneously to the right in an aqueous solution. In this system, the strongest acid is, well, let's identify it. The fact that it says that the reaction proceeds spontaneously to the right, this tells me that the products are favored. Spontaneously to the right means products favored. If it said spontaneously to the left, I know my reactants were favored. Or in other terms, if it said it was non-spontaneously or non-spontaneous in the forward direction, then my reactants would be favored. However, it proceeds spontaneously to the right. And we know that the equilibrium favors the formation of the weaker acid and base. So because the reaction is going this way spontaneously, we know that the weaker acid and base are on your right, and your stronger acid and base are on your left. So let's identify the acids and bases, and we'll be done this problem. So HSO4 minus, that's your acid. CO3 minus was the base. SO4 minus was your conjugate base. And HCO3 minus is your conjugate acid. We want to know what the strongest acid is. We know the strong side is the left side, reactant side. HSO4 minus happens to be the acid on the left, so we've answered the question. (16.3) deals with the autoionization of water. This simply means that water can react with itself to donate a proton to another water molecule. So you have two water molecules reacting with each other to produce hydronium and hydroxide. This happens because water is amphoteric. It can accept and donate a proton. What you need to know about this is that we can write an equilibrium constant expression for this, and that is Kw. It's W because it's for water, right? Just gets a special subscript. Normally it would be products over reactants, but we don't write the reactants because we only use aqueous phase labels in our equilibrium expression. We do not write liquids in. So you can think of it like this. Over 1. So we don't have to write this 1 business here. So that's your Kw expression. What you need to know that this is a very small number. This is measured at 25 degrees Celsius. All K values are temperature dependent. The important thing is it's a tiny number. Look how tiny that is, 1 times 10 to the negative 14th. If that's 1 times 10 to the negative 14th and you do the math, that means in a sample of pure water, the hydronium concentration is 1 times 10 to the negative 7th molar. And the hydroxide ion concentration, 1 times 10 to the negative 7th molar. That's tiny. So what this tells us about the position of the equilibrium is it's so small, much less than 1, equilibrium favors the left side or the reactants. So 99.99999% of all water molecules exist in their unionized form, not the ionized form here. This is the concept to know. We're going to be using this equation, Kw equals hydronium times hydroxide, in the next section. All right, so using that equation, and its value, we want to calculate the H plus. Remember, H plus is equal to hydronium, so it's the same thing. H plus equals H3O plus. We want to calculate H plus if we know the hydroxide. Let's use the equation. We'll say H plus times OH minus equals 1 times 10 negative 14th. They're giving me the hydroxide. So H plus times 0.01 is 1 times 10 to the negative 14th. Do the math, and your H plus equals 1 times 10 to the negative 12. Now what if you want to calculate the hydroxide? Same thing. Let's use the equation. H plus H minus equals 1 times 10 to the negative 14th. They're giving us the H plus, so it's 2 times 10 to the negative 6th times the OH minus, which is 1 times 10 to the minus 14th. Do the math. Your hydroxide equals 5 times 10 to the negative 9 molar. These are molarities. Remember, whenever you see brackets, it means molarity.